Okay, so this is relational database system implementation. Seems like the, I don't know, does somebody want to hit like, there you go, a little better contrast. I guess these slides aren't very contrasty. But anyway, this class is focused on how relational databases work. And it's a project class, as you probably already know, so you get to have hands-on opportunities to explore various aspects of it, which generally has historically been fun for people. There's a few places where it becomes misery, but hopefully it won't be too bad. Yeah, so sequence of programming assignments. Right now it's looking like about 6. That's probably the minimum, the low end. And the high end will probably be something like 8. So you can already do math and say, oh, okay, well, 11 weeks total in the term, 6 to 8 assignments. You can probably see that it's probably not going to be too horrid as far as working is involved. So that's a good thing, I think. No midterm, no final exam. We actually hate them. I see a few of you celebrating. I hate coming up with them, and I hate grading them, and I know the TAs hate grading them as well. And really, when it comes down to it, you know, what I have always done as a software engineer is write code and get code working. And so that's, you know, sort of where my heart is. And so I'm glad if you guys are the same way. So anyway, we'll get to explore some of this stuff. Now, the prereqs, you should be familiar with SQL. There are a few people who have asked, I haven't taken 121, can I take 122? And as much as I would like to say, no, you must follow the prereqs, you really can do it as long as you know these things. So data definition, you should be familiar with that because you'll have to write some. Data manipulation, you should be very familiar with DML. And where can I put subqueries and all that kind of stuff. And you also should be familiar with the relational model and relational algebra. We will actually be talking about both of those things. Well, I should say relational algebra in particular quite a bit throughout the term. I will put up some of the relevant CS121 slides. Well, actually, you can access all of them from last term. They're all available in a nice, convenient, single location. And we'll actually be taking some of the relational algebra and extending it so that we can sort of figure out how to handle some of the nuances of SQL that we may encounter along the way. So things like subqueries. How do we lift subqueries up into the outer query so that we can execute them more quickly and so forth. So we'll have to extend the relational algebra to do that. Obviously, you'll need to know about things like sorting and searching. I'll give you the punchline of like, it's an underlying theme in the course. There's basically 2 ways to make things fast in data structures, but in databases in particular. If you think about your experience, you'll probably say, yes, this is true. They basically fall into sorting data and hashing data. So you have a search key and you sort on the search key, or you hash on the search key. And those are basically the 2 things. Data structures do it. Databases do it heavily. So you should be familiar with that kind of thing. Obviously, we'll go through a lot of details as we get through things, but you should have a general sense of how things work. And right now the database compiles in Java SE7. I was required to upgrade to SE8 for another project that I'm working on, so it'll probably compile under that as well. But I don't use a lot of the SE7 shortcuts. Like some of you may be familiar with how you can you can just put I call them angle brackets when it's less than greater than, but angle brackets for generics in Java. You can just have the compiler infer from the left-hand side what's on the right-hand side. I don't use that everywhere. If you feel like upgrading your code base, that's totally fine. It's not going to bother me. The secondary focus of the course, is also going to be software engineering. You'll see that we have a lot of tools that you'll get experience with. You'll have exposure to them. You won't necessarily learn all the little nuances of them. So Ant, has anybody here used Ant before? A few of you. So we use Ant for automated builds. You'll be happy because there's hundreds of source files. Documentation generation, JavaDoc kind of becomes your friend as well. It's largely well documented, but there's definitely areas where it's a black box. So while you have the source, so it's a clear box. But Then we have automated testing. I use the TestNG framework just for doing unit testing. And there's this really cute little project called Jacoco, which will tell you your test coverage. So you run your unit tests and it'll actually tell you what parts of your code actually were executed by the test. So that's really nice. You can find out your code coverage. That's what the COCO stands for. So find bugs for static analysis. We won't really care so much about that. Git will be your friend pretty much the whole term. And I already mentioned that there will be a repository for each team on the CMS cluster. If you decide to work somewhere else, like on GitHub or whatever, I don't care. The only request I make is that you would make your repository private. And since you are undergraduates in a class at an educational institute, then you can request private repositories from companies like GitHub without paying for them, which is like, yay for us. So, so I'd request that you make it private so that it's not generally accessible. But, and just make sure that you push your answers or your submissions to the repository on the cluster. That's fine. But that's where I'm going to be pulling the submissions. And then integrated development environments. IntelliJ IDEA is widely considered to be one of the absolute best integrated development environments for Java. So you won't go wrong installing it. They now have a community edition. They didn't for a long time, but they have for the last few years. It's excellent. So I think you'll like that as well. Okay, let's see. Yeah, so as would be obvious, there's a percentage of your assignment's grade will be based on whether or not your code will actually satisfy all of the testing. Now, this testing may be automated or may be manual. The TAs are hoping that I make it automated. I am too. But we'll see if I actually get there. Just be aware of that. And, of course, if you want to enhance the automated testing, you'll probably get bonus points for that because, it would be really helpful. Anyway, and all your work has to be clean and well documented. Now, when we say well documented, we don't mean explain every last little detail, because you should assume a basic knowledge of Java and of the problem domain when you're writing comments. So just be aware of that. You should follow coding conventions that you see in the code base. If you don't like them, I'm sorry. You'll have your whole rest of your life to write whatever kind of coding style you want, but please follow the coding style of the code base. It makes it easier to understand. JavaDoc to document the code you write, so that's pretty easy. You can just follow the pattern. I'm not really finicky about, do you have @param tags and @return tags and all that kind of stuff. I just want to make sure that everything is understandable. So if you need to write a JavaDoc comment, I'll typically say, hey, explain what you do for this, subtle thing in your JavaDoc comment, and it shouldn't be any harder than that. It's really important that your commit logs are useful. This is the #1 area where everybody in my project classes lose points. And it's so frustrating because it's not hard to do. It's super simple to write a little message when you commit stuff, and people decide not to do it. So you need to say what it is you did, and especially with Git, there's a specific formatting style that people are encouraged to follow. So I'll give you more details about that in your first assignment. But make sure that you don't forget to put commit logs in, or else you'll be sad, and I don't like taking away points. I love it when my students do well, so don't make me sad either. Any questions about any of this? Just general questions at this point. Okay, hopefully all of this is obvious and straightforward. Collab. Now, I actually like it when we encourage collaboration as opposed to discouraging it, because that's the way the rest of your life will work. So you will get to work in teams if you would like to. If you decide to go it alone, your life will probably be harder than most people, but certainly you can do that if you'd like. But you can have teams of up to 3 people, and I need to know your team composition. Now, I say by Friday, but since I was sick on Monday, it's looking like probably by over the weekend. So if you absolutely can't nail it down, then that's fine. But anyway, I will create repositories on the CMS cluster for you to use once I know your team composition. So far, I've heard from 3 teams or 4 teams, so I'm presuming a lot of people still will need to get that to me. And yeah, the assignments will be more difficult than they have been in the past. So whereas before, a reasonably capable person could finish things in 4 to 8 hours, now it will probably be significantly more involved than that, because the presumption is you'll have multiple people tackling it. So you're encouraged to work in teams. And that's obviously as much for us as it is for you guys, because there's no way that we can handle 60, 70 submissions, getting them all graded and reviewed. We have 2 TAs, so we need to be able to cut that down. Okay, yeah, so team submissions must be entirely their own work. You can think of teams as being like an individual, like corporations are individuals now. So, but you can help other people with tools or debugging and so forth. There's this sort of metaphor or analogy that's been floated as far as like collaborating, and that's the 50-foot rule. I don't know how much this will actually be necessary, but make sure that you don't share your code in helping other people diagnose their code. Look at their code and ask them questions and so forth. Mike has a great way of describing this. I don't know if he also described this at the CS1 organizational meeting this term, but when you're helping other people that are not on your team, you're acting as an informal TA for the course. So all of our TAs, we try to get, we tell them to help you think through the problems on your own, help you solve the problems, give you guidelines and clues, but not just give you the answer. So make sure that you're doing the same thing toward other people. And there'll be other details as well. All of that will be posted on the website. Yeah, so the other aspect of this is that we do expect teams to have roughly equal contribution as far as the code on the project. And when I say coding effort, you should understand that that doesn't mean necessarily everybody has the same number of changed lines in their commits, because that would be kind of dumb. So if you have, for example, somebody tackling a really challenging part of the code for that project, and they change 400 lines, and somebody else does something that's not as challenging, and they do 1,200 lines, that's fine. I mean, we care about coding effort. So just make sure that you're trying to keep it balanced in your team. There will be a design document you have to submit with each assignment. And part of this will be so that we can know what in the world you were thinking when you solved the problems. There will be optional problems as well, as you can see, but I'll talk about that in a second. But you will have to describe, well, what did each teammate do on this submission so that we can get a good sense of it. And like I said, the goal is that we see a roughly equal coding effort on each part, each assignment. And in general, as long as all of this is satisfied, we should see everybody on the team getting the same grade. I don't expect that we'll need to tweak this very often, but in cases where there's significant imbalances, we will have to. Okay? And obviously, design doc feedback will be one source of information about this. But Git logs are great. They say what files were changed and what lines were changed, and so we have scripts that can mine those things. So we can get a pretty good sense of what everybody's doing. So just try to keep it balanced. Make sure that it's an equal learning opportunity for everybody on each team. Okay, so that's kind of the goal. Anybody have any questions or comments or rage about that? Okay. Because, I'm still feeling out team projects for courses. So if you have any feedback about how this can be made better, please feel free to share it. Okay, assignments. So assignments will be all new this term. They're not all new, but they're mostly new. There's definitely going to be large new parts of them. So there may be some delays. And you should not be surprised by that. I'm going to try to stick to a schedule because I know you all need schedules to plan all of your other obscene amounts of work. What I want to do is make about 85% of each assignment, more or less, required. So that'll be stuff that you need to do for subsequent weeks. Like, it needs to work. And if you have stuff that's just completely broken, like you totally fail on a particular assignment, I want to make sure that we can give you guys working code just in case it completely breaks for you. So I will endeavor to do that. But 85% more or less will be required stuff. And then 15% of each assignment will be optional features or tasks that are interesting and nifty, but you get a choice. So you can say, well, I want to do this thing because that sounds more interesting. Or I want to do that thing. And that'll give you some flexibility in what you have to do. And hopefully that'll also give you all enough tasks that it's a pretty easy breakdown for each teammate to have some things to do. So anyway, that's kind of the goal. of the assignments. Obviously, there will be a lot more detail about this as we get into specific assignments. Course website. So many of you have already enrolled, but there's still like nearly half the class that hasn't. So you can get on the Caltech Moodle. The enrollment key is right ahead. If you haven't already enrolled, please do it now, because I will probably begin sending out messages about the class tomorrow or Friday, as early as, but it's unlikely, but possible. Just, you don't want to miss anything. Yeah, all the course policies will be there. I will definitely send a message when that is up so that you can read it, because everybody is individually responsible for being familiar with the course policies. And we have 2 teaching assistants right now. Because of that, I also, you may have noticed an invitation from Piazza. If you've used it before, then you're already familiar with generally what it does, but it's basically a question and answer forum for classes. And I found it to be useful for students to share information amongst each other. Don't post code of, like, here's my submission or anything like that. But if, like, NanoDB is a pretty large code base right now. It's probably one of the larger code bases you will be been thrust into unless you do Linux kernel hacking on the side for fun or profit or both. So, you know, if you're looking for help, like, what do I do to find this thing or that thing, then you can get on there and post questions, and hopefully other people will be able to answer. And hopefully Eric and Keshin and me will also be trolling on there and be able to help answer questions wherever they need to be answered. So we'll try to help you guys as much as possible. Late penalties, this is pretty typical for my classes. Extensions are also accepted. I forgot to update this, but you actually get 4 tokens, not 3. So I will. I base the number of tokens on how many I think you might actually need, and since this is like assignments are new and different and varied, I'll give you 4 tokens. So just be aware of that. Yes. That's a good question. Groups have tokens. Yeah, that's also an interesting challenge, because you'll have a group of 3 people, and one person will have gotten hit by a bus and gotten a dean's extension, and I have to figure out how to deal with those kind of situations. We'll wing it. Okay. So don't get hit by a bus just to get an extension. At worst, fake like you got hit by a bus. But yeah, so teams get yeah, so I'm sorry, teams. I will update this slide later. So any other questions? Okay. Okay. Yeah, so any questions about administrative aspects or anything like that of the course? All right, a lot of details will become evident when we actually get into the first assignment, like how you tag your repository so that you know, or so that we can pick up your submissions and so forth. We have scripts for a lot of this stuff from past years. Okay, now as far as the course itself, we care about relational databases this term. And you might say, well, what about NoSQL? Well, what about, is anybody going to say, what about XML databases? Probably not. Not anymore. But there's a lot of different kind of databases. Graph databases would be a great one to bring up. The way that I would put this is a lot of these ideas in relational database implementation carry over to a lot of these other database systems. And there's obviously different things and nuances that are special to those things. But if you know relational database implementation, you'll have probably 75 to 95% of your knowledge that you need for any of these other database systems. So that's pretty cool. Anyway, but tables or relations, we're going to be talking about tables. Like, you can pretty much, for this whole term, say, okay, in my head, relations now equal bags or multi-sets, not sets. We don't really care about sets anymore. Populated with rows or tuples, manipulated with SQL queries. So these are the things we need to provide. We need some kind of generalized query support. We need a data manipulation language. We will use SQL. You are lucky you do not have to write a parser for this, because SQL is kind of annoying. I have a parser that covers most of the language for you. How do we represent query plans internally? So we have to have some kind of abstract syntax tree internally. How do we optimize these plans? We're going to spend a couple of weeks talking about that all by itself. What plan transformations are allowed? We got a little bit of a peek at that in 121 when we talked about equivalence rules, but it gets so much richer than that. And what statistics do we need to guide that phase? We'll talk about some basic things. There's more sophisticated ways of doing it. How do we execute these things? So we have things like subqueries, in clauses, and exists clauses, and so forth. Correlated subqueries, things that so far the database is taking care of for us, but now we need to figure out how to take care of ourselves. Inserts, updates, and deletes, and so forth. And hopefully we will get to some advanced techniques. What really kindled my interest in database systems was working on a parallel database. So now you have n machines executing one query for you, and that was pretty amazing. There's lots of research about parallel database execution as well. Now we do need persistent storage. There are databases that are entirely in memory. I mean, I came from a world where having 64 gigs of RAM was like a pipe dream, but now that's not uncommon, and people do that relatively frequently. If you have an in-memory only database, that's great, but a lot of times it's just because you can derive that data from some source if you happen to have the machine explode. And so you do need persistent storage at some point. The only problem, of course, is that disks are slow. And if you've taken CS122, then well, spinning magnetic disks, or spinning rust as they're sometimes called, is probably 6 orders of magnitude slower than the processor. Okay, which is a lot slower. Was it the processor, or was it DRAM? And even solid-state drives are not that great, because they're still like 3 orders of magnitude to 4 orders of magnitude slower. So, even though they're nice, we need to have ways of interacting with the disk as little as possible. So how do we improve access performance? So we have various storage formats, data layouts. We'll spend quite a bit of time talking about that, actually. There's some really clever ideas for how to lay data out on disks so that you don't have to actually touch them very often or in very expensive ways. So that's neat. We have access paths, which we talked about a little bit in 121, indexes. And then, of course, you have RAID, which allows you to do, who here has worked with a RAID array? Probably quite a few of you. Yeah, so RAID is basically just a way of having multiple disks that you can access at once, and people almost always do this for performance. Because if I can have n devices that I can read in parallel, then I can read data faster than if I'm just dealing with one device. And then, of course, if you have these kinds of options, how does that factor back up into query planning? Because clearly I need to take advantage of them during my query planning. It may be that something that would be stupid to do on one disk starts to make a lot of sense if I have a solid-state drive as my temporary storage, and I can create some temp tables there and access them very efficiently. Okay. Also, we have transaction processing, which will be another big topic of the term. So we have these properties, ACID, which we talked about, unfortunately, toward the end of the term. And durability is one of my favorites. We'll be spending quite a bit of time talking about durability, where I basically finish some work. And by finish, I mean that the database said, yes, I have committed your transaction. So I asked it to commit it, and the database said, yes, it's committed. And then the power fails, somebody yanks the plug out of the computer, the CPU explodes. Who knows what causes the database to die. But let's just presume for a second that the storage is unaffected. Well, I should be able to restart that system, and all of my committed transactions should still be there. And furthermore, anything that was uncommitted should be removed. Okay, so that's a pretty high standard, and we'll talk about how to achieve this. You'll actually have a whole lab where you get to learn how to do this. It's kind of fun. Consistency, so you have a multi-step operation, and along the way you violated constraints. Well, the database should roll back all the other changes that the transaction has made. And then, of course, we have isolation. So we have concurrent access, and NanoDB just barely has concurrent access, so hopefully by the time we get to that lab, it'll be the last lab that we will probably do. If you have concurrent access, how do you make sure that these concurrent interactions don't trample each other in horrible ways? Okay? And of course, that gets down to the I in ACID, isolation, and we have a lot of different definitions for isolation. And we have about 5 that are in common use right now. Remember, we talked about some of them: read uncommitted, read committed, repeatable read. We have snapshot isolation, which most databases do, and then serializable, which is sort of the pinnacle, but it's very slow. So how do we implement isolation? We'll talk about that as well. Okay, yeah, and so that can actually affect query planning as well. We probably won't talk about that in as much detail. So if you want to explore some of these things, like what I want you to do to think about throughout the term is as we're going through some of these topics, think about if you are interested enough to explore them in 123. Like if you plan on doing CS123, there's a lot of really interesting topics, and I'm going to be making a list. I always try to make a list as we go through the term of interesting things you could implement in CS123. And but keep an eye open for it yourself if there's a certain area that happens to be particularly interesting. Okay, so this is the basic architecture of databases. A lot of databases include boxes other than the ones that we're listing, and some include fewer boxes, but these are generally the boxes you'll see in a database. So we have the files on disk, so that's the file system down below the dotted line. So your operating system is managing that, you have hardware managing that, and these files are read and written in blocks so that we can improve performance. And it makes a lot of aspects of the system easier to think about because you just have 4 kilobyte blocks. You don't actually think about it as columns within a tuple or so forth. Now there's a component called the file manager which sits and provides all of our various file-based operations. Okay, so I want to create a file, and I want to read the first block of it. Or I need to read the 15th block, and it doesn't exist yet, so I need to extend the file's size to include 15 blocks, and so forth. So that's what the file manager does. It's very basic. There's a few other operations it provides as well that are really important for transaction processing, like make sure all of this file's changes get written to the platter. We'll talk about the importance of that in just a few lectures, actually, because it's very important. Then you have the buffer manager, because remember, everything that the file manager does is slow. So if everything the file manager does is slow, then we want it to be invoked as little as possible. So we introduce another component above it called the buffer manager, which basically allows us to control how much memory is allocated to various queries, and also make sure that the most frequently used, or whatever what's it called? Yeah, whatever the policy is, that's the word I'm looking for. Whatever policy we want for evicting pages is followed so that basically the most important pages are kept in memory and less important pages are pushed back out to the file system. So the buffer manager is very important for that. Yeah, and so in general, for example, what you'll find is that your data definitions are in memory, because they're accessed a lot. We need to know what the schema of a table is, so that's going to be accessed a lot. In your indexes, remember, we generally have B-tree indexes, so the root index page will be in memory most of the time. So there's certain things that are almost always in the buffer manager. Now, the one challenge the buffer manager has is that it doesn't know what everybody else's changes are. And it doesn't really keep track of that very well. It only has one job, and that is to cache pages and allocate pages in memory for pages in data files and so forth. So it works closely with another component, the transaction manager, to make sure that all of our ACID guarantees are actually provided by our system. So yeah, pages are written back to disk in a way that satisfies transaction properties. We won't care about this for a lot of the term because we'll have a single user on the database system. But as we get further along, suddenly we'll start caring about, well, what pages are written back and what order are they written back? Are there pages we can't write back because it would be a bad idea to do so? There's a particular rule that I have just a little hint of here. So dirty pages cannot be written back to the disk until the transaction logs are properly updated. There's a rule called the write-ahead log rule, which says that pages can't be written back to disk until the write-ahead log reflects those pages' changes. Well, the buffer manager works closely with the transaction manager to make sure that those things occur properly. Okay, so that's that. Now these things together basically comprise the storage manager. Now, NanoDB has a couple of new boxes, they really only add abstractions, the table manager and the index manager, which allow you to manage various kinds of tables and so forth. But these things basically comprise the storage manager. And you'll notice that anything that involves working with data on the disk is covered by the storage manager. Okay. Pretty straightforward. Now on top of this, we have two things that we need to provide. We have data definition and data manipulation. Now data definition, we don't really do anything very clever for it. In fact, if you think about data definition, most of the time we need to just go and update a few things here or there. If we were really cool, I don't want to get ahead of myself, but you'll see this box data dictionary. If we were really cool, then we would have a data dictionary in NanoDB, but we don't have one. And the DDL interpreter would just say, oh, somebody wants to create a table, so I'm going to go add the appropriate records into the data dictionary. Somebody's dropping a table, so I need to go and drop the appropriate records out of the data dictionary. So generally, we don't need to do all kinds of joins and subqueries and all that kind of stuff. So we don't really care about it. We just implement it in very easy interpreter. And like I say here, many databases don't even have transacted data definition. So there's not a need to actually invoke a lot of the complexity that we do for queries. Okay, so that's that. I can't remember. Yeah, MySQL doesn't have transacted DDL. Postgres does. Postgres is actually really good about this stuff. So NanoDB could, and I think that's going to be one of the optional tasks if somebody wants to do it, because what you basically need to do is add the ability to transact creating files, dropping files, and so forth. And then you should be able to transact DDL as well as DML in NanoDB. So if somebody wants to do that, we'll get there. And that would be a cool thing to implement. So yeah, data dictionary, table files, and index files. So this is what data definition operations require you to do. So I want to create a table. Well, that's pretty straightforward. I just create the table file for it, make sure that the schema is stored somewhere. Okay, and let me see what I say here, because I don't want to get ahead of myself. This data dictionary thing is actually really important. You may have noticed that some databases include this thing called information schema. Has anybody noticed that there's this whole set of tables and so forth? A lot of SQL databases have it. When you're in MySQL, check for it. If you're in Postgres, check for it. Oracle has it. SQL Server has it. It's basically a SQL standard now that says you can ask this table for a list of all the tables in the database. You can ask this table for a list of the columns in all the tables in the database. You can ask this table for a list of the indexes. And that basically makes it very easy to discover the schema that's stored in a particular database. So that's what the data dictionary basically encapsulates. And it makes sense, right? Because I'm building this thing that allows me to create tables that hold rows of data. So why not use that mechanism to store schema? I think it makes a lot of sense. NanoDB doesn't have this though, so just be aware of that, but we'll get there. Anyway, so you can see how creating a table would be inserting some records into these various tables in the data dictionary. And furthermore, creating a file that corresponds to the table and making sure that that's associated with the table data and so forth. So there's a few little details there. And probably the most important detail of all of this is the last point, which is we don't use the query processing system to do this stuff because it's very simple. Add a row, remove a row, change a row, maybe add multiple rows to the columns part of the data dictionary, but that's about it. Okay, so that's data definition. Queries can be complex and time-consuming. I think you guys finally started to get a hint of that on assignment 7 and 8, especially when I started discovering runaway queries, which was great. I actually figured out how to write a script to check periodically for runaway queries so that next time we teach 121, I'll just leave that thing running and it'll just kill runaway queries periodically. It was kind of funny. But anyway, even on a good day, some queries take a long time to run. And so that's the part that the query evaluator is responsible for taking care of. So we have these plans that we come up with. We take SQL as the input, and we turn it into an execution plan of some kind. And then that thing has to be executed, and that's what the query evaluator is responsible for. And you'll notice that there is a very strong correspondence. I say loosely based on the relational algebra operators. What I mean by that is a plan node may encapsulate 2 or 3 different relational algebra operations in one. Like all of our joins basically can do inner joins and whatever outer joins they're most capable of doing. Like nested loop join is a really simple join algorithm, but it can't do full outer join. So we don't implement it. And there's a few other operations as well that we need to support, like semi-joins for supporting subqueries. So you'll see one plan node that's able to do a lot of different things. You'll see select can also rename the output. So you'll have some set of operations that are encapsulated in a plan node. And they will all access the storage manager, so they all basically interact directly with the storage manager. Hey, give me this table. I need to start traversing the records in this table. I need to look up a record in this table, and so forth. So that's what the query evaluators plan nodes basically interact with. On top of that, we have the thing that parses the SQL and takes the SQL and massages it until it's happy with the SQL, and then passes that SQL into the planner proper, which takes it and turns it into a bunch of plan nodes. Okay? And so we'll talk about how that works. That's actually going to be a couple of weeks worth of coverage. So we'll spend quite a bit of time talking about that. But this is the thing that's responsible for generating an optimized execution plan, or a not optimized execution plan, as your planner will probably start out. And like I say here, you use a combination of guessing and statistics. Your statistics hopefully are accurate, but they may not be. And your guesses may be accurate, but they may not be as well. So you do the best that you can and come up with a guess as to what plan is best, and then you go ahead and execute it. All right? Are there any questions about anything in this picture so far? All right. I think most of this is conceptually straightforward. It's how you build each one of these boxes that starts to get a little bit complicated. Of these, the file manager is probably the simplest. Yeah, and then everything gets more and more complicated from there. Okay, so we will be using NanoDB. I've mentioned this a few times, but this is a database that I've implemented in Java, and you might say, why Java? And we could probably have a whole class about that, and it would probably be more of an open discussion than that. It's interesting because database implementation covers all the way down to interacting with disks directly, up to symbolic manipulation of expressions and queries and optimization and stuff like that. There's not a lot of languages that are really good at that kind of thing, at that whole gamut of stuff. Now, there is one I know of, OCaml. How many people here know OCaml? Yeah, this is why we're not using OCaml. So, yeah, I mean, so this is the challenge of building a system. Now, Python actually wouldn't be a bad choice, but the reality is that most databases are implemented in C or C++. So Java is of similar, it's in the same sort of family as those other languages. So you get a lot of the same implementation annoyances and details, but you don't have seg faults where your program just dies and you don't know why. So I figured that Java was reasonable enough to do that. If you want to complain about it, you must suggest a better language too. I'm not going to just take random complaints about this. And so the primary focus of NanoDB. You might also ask, well, why didn't you use Postgres? Anybody who asks that probably hasn't been in the Postgres code base. Okay? And I spent 1.5 years in it. So, but yeah, the main thing is that most of the open source databases are not designed to be comprehensible. You might ask, why not MySQL? And you'll know the answer to that pretty quickly. MySQL is not very, what's the best way to put it? I have to be careful so I don't sound like I'm just slamming it. But it's not implemented in a very extensible way that allows you to do some really cool database system stuff. MySQL is implemented around some very simple concepts which do the job most of the time, but there's a lot of things that they cut off. Like, why can't MySQL do full outer joins? The reason why is because its entire join processor is built around nested loops. It can't do any other kind of join. So, sorry, that's just the way MySQL is. Anyway, so NanoDB tries to be comprehensible. It has a lot of logging, documentation as much as I could put together. So hopefully that'll be helpful. But it is a work in progress, and sort of the number one thing I can say about this is you will see a lot of to-dos in the code base. Do not think you have to implement every to-do. Those are mostly for me. Okay? If you see a to-do and it's not actually specifically mentioned in the assignment, then you're probably safe. And if you're not sure about that, ask me or ask a TA. But there's a lot of work that's ongoing, and I feel kind of bad that you're seeing it in the state that it's in, but it is what it is. It's a project that's being done by one guy in his spare time. So it is what it is. Okay, so database stores data in files, manipulates data in memory. So we have data stored on physical devices. We do need to understand the characteristics of these devices. It's funny because most of database implementation is how to interact with disks as efficiently as possible. That's like so much of how these algorithms are implemented and so forth is guided by storage limitations. So there's a lot of different storage media available. If you've taken CS24, you've probably seen some characterization of storage media, and this certainly will not vary too much from that, or the OS class. We talk about some of this in the OS class as well. As far as databases are concerned, these are the characteristics we care about. Access speed, cost per unit storage, because generally, remember, we have a lot of data we need to manage, and reliability. And also, different media support different access patterns. Okay? DRAM is accessible in very different ways than a magnetic tape. Okay? Probably most of you have not worked with magnetic tape for data storage. That has a very specific access pattern that you can really use it for. Has anybody actually used magnetic tapes for anything? Okay, wow, this is just sort of like 21st century stuff. Tapes are still actually relatively frequently used for storage, like backup storage, like if you want to do offsite backups or something like that. So, it's nice, but sequential access is basically all you can do, okay? Efficiently anyway. And that is the reason why TAR exists, too, by the way, if you didn't know what TAR stands for, Tape Archive. Then you have DRAM and flash memory, which are very good for random access, and then you have disks, which are kind of good for random access. But some random accesses are faster than others. So it's kind of an interesting thing. We also can categorize things as primary, secondary, and tertiary. So primary storage, your cache and main memory fall into this category. Cache memory is small and fast. We typically don't design databases with cache memory in mind unless we're companies like Oracle or Microsoft or IBM. Okay? Because they have long histories in their projects. They have the time to optimize to that level. NanoDB is definitely not optimized this way. And there's probably areas of Postgres and MySQL that are, but it tends to be uncommon. Main memory, much larger than the cache, but too small to hold the entire database in general. Okay. And it supports random access, which we also call direct access. What we mean when we say direct access is I give the address and I can access that value immediately. If you think about that in comparison to a magnetic tape, I give an address, well now I need to seek for 45 seconds to get to the data. That's not direct access. You have to go to it. Storage is volatile. If the power goes out, the data does not survive. Then you have secondary storage, aka online storage, and by online we mean that it is accessible automatically without human intervention by the computer. So secondary storage is larger, cheaper, and slower than primary storage, and it is persistent. So anything that makes it to the disk platter or makes it into your little NAND flash memory chips will be there after a power outage. And so magnetic disks are a very common form of secondary storage. We're going to spend most of the class talking about magnetic disks, even though probably most of you have solid-state drives. Because most database servers still use magnetic disks. And then flash memory devices, which we will talk about some, they are becoming increasingly common, but they tend to be used for less large data storage. We should probably try to characterize that more specifically. Okay, then you have tertiary storage or offline storage, and so this would be like your archival data. So optical storage, your CDs, DVDs, people don't usually use CDs very much anymore, but DVDs are still used pretty frequently for optical backups and so forth. Tape storage, and the access rates are very, very slow, even compared to secondary storage. These things can be managed in a library. I kind of mentioned this a little bit when we were talking about data warehousing. But there's these robotic systems that people have that they build for swapping tapes in and out. And so that's actually got a different name. It's called nearline storage, where basically the computer can initiate the tape swap. And so that's nearline. But it still may take, a minute or so for the data to become available. I should say for a minute for the tape to become available, and then you need to actually scan through the data until you get to the data you want. So that would be, a couple minutes, and then the data is available. So that's nearline. Offline is a human being has to go get the tape and put it into the drive for the computer. Okay, so that's a very simple description of the storage hierarchy. This is another picture. You guys have all seen this kind of picture before, so it's certainly not new. Are there any questions? Okay, so let me see. Cache main memory, flash memory, magnetic disk. Let's see. Optical disk and magnetic tapes. Yeah, so this higher you go, it's faster, but it's more expensive, and it tends to be smaller because of the cost. And as you go down, then it's cheaper, slower, and larger. Okay, so we'll start talking about magnetic disks. You may already generally be familiar with how magnetic disks work, but we'll talk about their layout and their structure, because this will become important in how we design our database. So like I have here, you have typically multiple platters mounted on a single spindle, or rotor, if you will. But basically all the platters spin at the same constant rate, because they have to. They're all stuck together. And you would sometimes see 5,400 RPM hard disks. This would typically be in your laptops, because if it's spinning slower, it takes less energy to keep it spinning. 10,000, 15,000 RPM tends to be what you see in database servers. Like the 121 database server was like a 10,000 RPM disk. Just one of them, but that tended to be sufficient for everybody's needs. Okay, so you have the platters, and typically both the top and the bottom are used. And so you'll see 3 or 5 platters, and it's kind of funny because you may notice, like, ooh, we have a new larger hard disk, and it's this much larger in gigabytes or terabytes, and it tends to be that they found a way to cram another platter in, so you'll see that it goes up in multiples, or sometimes when they actually change the storage technology, then it'll go up in some other way, but then they figure out how to cram more platters into the drives. So you tend to notice that the sizes change in kind of predictable ways. Now you have a disk arm, and basically you have heads mounted on that disk arm that all slew together. So I have these various read-write heads, and there's obviously one for the top of the platter and one for the bottom of the platter, and then for the next platter I've got one for the top and one for the bottom, and so forth. And so I have a little actuator on the disk arm assembly, and the spindle is just spinning at some constant rate. So this is basically what's going on. Now these platters are divided up into tracks. You can see a track is just everything is at the same distance out from the spindle. Okay, so that's a track. And tracks individually are divided into sectors. And it used to be that you always had the same number of sectors whether you were at the inside of the disk or the outside of the disk. Because there were kind of 2 challenges that you ran into. One is that the disk surface was going under the head faster at the outside than at the inside. And the second thing, so you have that same, whatever that physical medium is, you have more of it that's going under the head. So the data's coming off of it faster. And so it used to be that you just had a fixed number of sectors all the way from the inside all the way to the outside. As the computer hardware has gotten more and more sophisticated, now we cram more tracks toward the outside of the disk. And so you actually get your fastest reads from the outside of the disk as opposed to the inside of the disk. The way that they do it is they'll divide each platter into zones, and each zone has a fixed number of sectors. And so they may have 5 zones or 7 zones, and each zone will have a specific sector layout. Okay, so all the heads are positioned by one assembly, which means that you have the same track on each platter is going to be accessed at the same time. So those tracks together form a cylinder. Okay, so a cylinder is just the tracks at the same distance from the center on all the different platters, because those we access all at the same time. And when you want to read a sector from the disk, the hard disk does some quick math and figures out, well, what cylinder is that in? What platter do I care about? What sectors do I need to access? And it will basically slew the disk arm to the appropriate cylinder. And then when the sector passes underneath the head, it will read the data, or it will write the data. So you see that there's a number of things that have to happen. Okay? Any questions so far? But this is what's happening when your computer is chattering. So there's various performance measures that we can think about when it comes to these kinds of magnetic disks. You have access time, which is just I issue a read or I issue a write, and then the disk tells me that the read or the write is completed. Okay. And so, like it says here, the read-write heads have to be moved to the appropriate track, and then the sectors have to rotate past the read-write heads. So that first operation is called a seek. We always call it a seek. And you typically see on disks, you'll see the average seek time. What's the average seek time of this drive? Okay. What they do is they do a whole bunch of random seeks, and they figure out the average. Okay. Rocket science, right? But generally that'll tell you this drive is faster or slower at seeking. Now, we don't want to do that. That, like, in our ideal, we don't have our database server slewing all over the disk for every little operation. And so what you need to think about is, well, how can we lay out data so that we can take small steps on the disk instead of big steps? And so typically what you'll see is we try to lay out data and then we try to access data in ways that minimize our seek time. And it really doesn't, the only reason I'm mentioning this now is that we don't think about that in terms of average seek time. We think about this in how much time does it take to seek from one track to the next, one cylinder to the next, to the adjacent cylinder. Okay? So I just want to make sure I mention that as a note. But the average seek time is a good general measure of disk performance, disk seek performance anyway. Okay, rotational latency time. This is how much time does it take for our data to actually get to the head. And you can see that, well, I may perform my read and the data is just coming to me so I can read it. Or I may issue the read just as the data is getting away from me. So I may either get it right away or I may have to wait a whole revolution. So the average over time is going to be half the time for a full rotation. And so you can see why I'd like the disk to spin faster so that I can get the data off the disk more quickly. That's why we have 10,000, 15,000 RPM disks. Okay, and then of course you also have the fact that disks can only provide data so rapidly onto the data bus of the system. Okay, and so that's the data transfer rate. And interfaces will go up to 600 megabytes per second. Gigs. It's gigabits, but it's not gigabytes. So it's 600 or more megabytes per second. But the disk itself can limit that. The I/O subsystem on the motherboard can limit that as well. So you may have, for a single disk, you may see anywhere from 40 megabytes a second up to 100 megabytes per second for RAID. You might see multiple hundreds of megabytes for RAID using solid-state drives. You may even get higher than that. It's certainly possible to get higher than that. Okay, any questions? Okay, I think that, let me see what the next slide is. Yeah, so what we're going to do is we'll wrap it up here, because my voice is going anyway. And we'll pick this up on Friday and go into more storage layer details.